And they're classic interview questions as well as classic examination questions. So we'll do that quickly as a revision. Remember, I did not start with those things. I started straight with camera design, because I know all of you guys have used cameras in your past. But we need to know some of these fundamental terms, because right now I was doing a qualitative design of the system. I was not going into the exact nitty-gritties. Right? I was saying, here's a pixel circuit, this is how it works. Here's a MEMS circuit, this is how it works, not necessarily on how to build them. So we will do that as the first exercise. The second exercise we will do would be to see how can we translate all these mechanical, chemical sensor into their electrical equivalent. Because if I can redraw that mechanical circuit as an electrical circuit, I can understand it. So I'm talking purely from electrical engineering point. And by electrical, I mean electronics as well. I know in India we separate electrical and electronics as two different disciplines. It's the same from my point of view. Right? So we will translate all of these mechanical circuits or mechanical systems or chemical system into an electrical equivalent and then design using the electrical circuit. Okay? Any questions for today? If not, highly recommended book will be Microsystems Defined by Steven Centuria. There are also books by Joshi, which is I have used, which is the EPJ. I have used the EPJ technical, the journal, EP Journal on Technical Instrumentation for the MEMS, for the damping part of this lecture. And I have used some of the pictures from Micro Machines journal by Aplo Bhavid. And today we have gone through a little bit of microelectromechanical system from a resonator perspective. In future, we will also see them from a gyroscope perspective, from an accelerometer perspective. The sensors are not terribly different, but the design approach is different. Right now, we are looking at the individual motion, x or x dot. In future, we would like to see their acceleration. Okay? With that, I have been asked to stop at 12:30 today for a meeting, and I will stop now. I wish you good luck. In the afternoon, we'll meet at again 2:30ish, and we'll meet in the lab. Okay, we'll finish that design possible. The morning was wide dynamic range pixels, and I used the techniques which I have used to make wide dynamic range pixel. But that was a bit unfair. I should also tell you what other people do. Okay. Oopsie, not my computer. So the classic problem is this. We have got, for low light, our pixel works fine. For high light, it integrates completely. Now we tried to make it as a logarithmic pixel, or we tried to do some sort of a linear and logarithmic together. That's not the only way you can look at the problem at. One thing which you could do is you could just increase the VDD. Right? If I give a big voltage sweep for it to fall down, I will get a high dynamic range anyway. Of course, increasing VDD is not advisable because that comes at the cost of power dissipation. So, other thing which could happen is what happens when this charge, this well fills with photocharges. When it saturates, what happens to charge after that? It spills, it goes somewhere else, either goes to the neighboring pixel or spills through the reset device. So one operation which we could do is to change the reset voltage every now and then and see if it gives it extra charge. There are many ways people have done. There is one circuit which is this. Essentially what you do here is you have got a separate capacitor to integrate the charge being produced by the photodiode. But you do not send all the charge. You send some charge to the capacitor, and then, now this is a common gate amplifier, okay? So what you do is you change the saturation level every time you reset it again. And you do something like this. My For low photocurrent, okay, I get typical things. As soon as I saturate for the high photocurrent, I reset the pixel, so it starts again. Then I reset the pixel, so I get a waveform, comes some sort of a non-linear compounding waveform for this. So the design which people did, this was Charles Soudini's design along with his student Decker. They had 8 analog voltages, and despite doing all of this, they only got 96 dB of dynamic range. Remember, a normal image sensor has about 60 to 80 dB of dynamic range. The human eye does anything from 120 to 180 dB. So from lowest level of 1, we can see up to 10 to the power 6 or 10 to the power 9 luxes. The other problem with these are, because it's a non-linear stepped response, how do we make color out of it? Is an open question for us. Other approaches people have done is don't change the saturation level, but what you do is you take the spilled charge and integrate it again. So use the same diode, so you integrate first your normal value, and then after that you reset it and you integrate the spilled charge as a separate incidence. So essentially you do 2-stage integration, one for normal and one for whatever extra charge which is left there. There's another approach by Akahame and co-workers. What they did was they added another capacitance here, and the idea here was you have got a gate to the pixel, and then you decide what charge goes here and what charge stays here. There are multiple approaches on the same thing. The whole idea was we have large amount of photo charge that's saturating. Can I divide it into 2 chunks and do elsewhere? Here was another approach, and this was much simpler. Essentially what you do, midway during integration, you soft reset all the pixels, and then restart integration again. So if you keep on soft resetting it, the pixel will never saturate. People have also tried putting 2 different type of photo devices, a photo gate and a photo diode together, moving charge from one to another, and that also increases the well capacity. So all of these type of high dynamic range sensors are called well capacity increasing sensors. So my diode has limited well capacity. We try to increase the well capacity by adding something or the other. The other approach which we saw yesterday was dual and multiple sampling. Take the same scene many times, and I went very, very quickly there. So question still says, how do you store these multiple samplings? So Yarit Peck from Technion, she uses 2 capacitor banks, and each capacitor bank stores the output voltage from 2 different integration values. Okay. El Gamal from Stanford, he used an in-pixel ADC, and what he does is that he samples the pixel's response at many times, but these times are exponentially increasing. So first he samples at time 2t, then at 2t, then at 4t, then at 8t, then at 16t. Okay. And then he he integrates this as the digital response of this thing. There are also other people who are trying to find, rather than integrating each pixel, what would be the optimum time a pixel should be integrated. So initially we said, okay, 20 frames per second, we integrated for 50 milliseconds. But if we know the average intensity in the scene, then we could change this integration time. So if we know our scene is dark, then we integrate it for longer. If we know our scene is bright, we integrate it for shorter. Now that could be done in many ways. There are circuit-based approaches, there are algorithmic-based approaches to find what's the maximum integration time in which none of my pixels will saturate. Acosta Serafini and colleagues, they try to find, they have got these integration slots. During the integration time, they check the pixel at every few instances. Is it going to saturate? Is it going to saturate? Is it going to saturate? If it is going to saturate, integration, if it's increase the integration window. The circuits are very similar to active pixel sensors here. All that you have is an extra SRAM per pixel to help you find these things. Belankey and co-workers also put a static and dynamic in-pixel memory to do the same operation. So we looked at changing the well capacity. We looked at doing dual and multiple sampling. The other approach which we could look at is this integration time control, right? We talked about where. So you can do it for all the pixels at one go, but that means, okay, we had one bright scene, one part of the scene, all my dark also changes with that. Okay. So another approach could be, we don't do for the whole imager, we do it for local areas. So now in this area my scene is dark, I integrate it for longer. In that area it's bright, I integrate it for shorter. So there have been couple of approaches wherein people have compared. So while it's integrating, you go and look at in each region till where my pixel has gone in, and then you adapt the integration time based on that. So here is one circuit which does that. I must confess this is slightly wrong. It's a PMOS level circuit, so it's exactly the inverted circuit. Remember, the pixel which you are having, you have NMOS on top and NMOS read. There's no reason to do NMOS. You can do a PMOS circuit as well. You can have diode on top. So here the diode end is connected to VDD, and then you have PMOS, and now you are resetting it. This is a PMOS, my apologies, to ground. Okay, so rather than the signal coming down, the signal will be going up now. So in the inverse is also, generally we don't use PMOSs because they take quite a lot of area and they come up with, and they are slower compared to NMOS. There has been other alternative approach. This is Breidenthal, wherein they reset every row at a time. They look at how much is a row taking to integrate. Okay, and they adapt the integration time of each row, and they store how much, at which stage this adaptation happened. Zarandi and co-workers, they put a latch inside each pixel, which then determines, is my pixel integrating for long or is my pixel integrating for short. Few other people have tried putting a column amplifiers in the column. I'm going to a bit longer because there is no use to study detail. They are all patented design for individual groups. But it's good to see that it's not just one approach. There are other approaches to solving the same problem. So here they have put a standard active pixel sensor, but in the column we have an amplifier to check what's happening to each pixel. And now you change the gain of the column amplifier rather than the pixel itself to figure out how it is going faster. In all of these integration time control approaches, we suffer from fixed pattern noise. And all of these we have difficulty on how do we reproduce color. You have to do additional pre-processing in advance to find what's the optimal integration time. You have to do additional post-processing in it later on. The next approach, and there will be just a couple of more approaches I will talk about, are approaches which look at, rather than changing the integration time, can we fix a threshold and see how long it takes for my integration value to reach there? So I measure a time. Okay, right now typically we are measuring voltages. Rather than measuring voltage, why don't we measure a time it takes to reach a threshold voltage? Okay, and there have been many such approaches. Essentially you put kind of a comparator inside the pixels, see till where I have reached. So one of the pixels which I showed you in the morning, our design was also a threshold comparing pixel, but rather than fixing threshold, I was changing my threshold. So people have tried putting a threshold comparison in each pixel or in each row, and then you have got a reset register as soon as, so people have also done a mix and match of this thing. So I measure it to a threshold in a frame. If my pixel has not reached it here, I allow it to integrate. If my pixel has reached midway, I reset my pixel. Okay? So if I reset my pixel, it starts from the beginning again. So many such approaches have been tried. The third approach is that of counting. So I only count how long it takes for my pixel to reach here. So as soon as my pixels start, I start a counter. I start counting the number of pulses. My pixel reaches here, that's the count I have got. Now, two advantages here, it's automatically converting to digital as well. Okay. So Ando and co-workers, they have put 1-bit ADC per pixel, and you can design a 1-bit ADC with series of inverters. They have used a 5 inverter, and the moment my pixel hits that threshold, it sends a high signal to be stored in a reset switch, that I reach that threshold, and then I reset my pixel. So I do 2-stage integration here. The design which I used to love quite a lot, which was very complex for me to understand, was David Stopa design from FBK in Italy. And they did a very interesting thing. They have 2 time clock pulses in the pixel, one which does fine measurement, another which does coarse measurement. So they have something like this, when they are having 2 ramps, one ramp which keeps on going up and down, and the other ramp which is going at a more leisurely pace. And you are then trying to find where is my pixel reaching in both of these, between these 2 ramps. Okay? And by doing this thing, they are essentially recording the fine time and the coarse time which is needing to reach a certain threshold voltage. The problem with all of these pixels is the computational circuitry required to manage the pixel is quite complex. So classic log pixels, like the one which I showed you in the morning, here is a log pixel with a bipolar junction transistor here, rather than a diode, which people have tried. The classic log and linear log pixel is still one of the better ways of doing log approaches. Remember, when we were doing our tutorials, I talked about FPN correction. So this is my doctoral work. This is the circuit we had there. That's your diode, that's the switch, and that's the calibration current source. So that by controlling that current source, I can determine what current will flow here, and I can use that current to calibrate my diode. There's something else which we have done here. Remember, the model was y is equal to a plus b log x. And I kept on saying source follower does not have a unity gain. It has a small gain. So if my gain is small, any small error will lead to a big error. So one thing I could do is I could increase the gain in my output chain, so that even if there is a small error, it causes less effect. So this is one of the circuit we did. We did not change the pixel. The pixel remains as it is. It looks like a source follower plus row select. But on the other side, in column, we mirror it and we form a differential amplifier. So you have got a PMOS load there, this is matched, and then you have a column bias. We can design a differential amplifier to have a unity gain. A source follower will always have lower than 1 gain. So in your circuit, you all are having a simple source follower readout. If we keep both of them exactly the same, but rather than connecting this to VDD, we connect it to the load to get a differential amplifier performance, we can get a higher gain, and that reduces the our desire to improve on the gain mismatch. Just few more things before I let you go and do the lab work, and then we'll break again in half an hour to do the sensor circuitry work. Log pixel has a problem in low light region. As we start going, it doesn't go straight to 0. You see this smooth bend? So here I have got decent sensitivity. My X changes by something, my Y is also changing by that. In this region, there is a smooth bend. So my X is changing, but my Y is changing by a very little amount. So when I have got low light, log pixel have got low sensitivity. This is also the reason why we started doing lin log pixel in the morning, something which is linear, linear at low light, logarithmic at high light. And just before, I want to let you guys, this is the kind of response we received from our pixel. This is individual pixel measurement. Of course, it's a bit noisy measurement. So for high light, I was getting this low intensity. Then for medium intensity, remember it's saturating, but medium intensity and high intensity has not saturated at the same time. In our standard pixel, all of them would go all the way till here and saturate. Okay. So because I'm doing a logarithmic conversion, low light remains linear. After that, I get a logarithmic response. So what I would advise you guys to simulate, if you are having difficulty in simulating your linear pixel, let's make it a log pixel. And that would be fairly easy to simulate. Okay? There is no time information to be fed, no current information to be fed. Of course, you need a biasing circuitry, but you do have a, just provide a photocurrent in parallel to your diode, and you are done. So you know you have got a reset switch. Remove reset, connect the reset to VDD. That also removes one circuit which you need to draw in your layout. So life would be easier there. So I'll leave the circuit. So essentially we want this part of the circuitry. So now you only have one line going into the pixel, the VDD. Convert this to VDD, ignore the reset part. Let's just have this part here. VDD and row select, and we are done. Okay. There will be one trick which you will have to do. This I think will be helpful to people who do VLSI here. It will show very high leakage current. The simulation by itself will show you very high leakage current. It took me a year to figure out why it does that. It's got nothing to do with heat generation. What's the photo current level we are seeing? Femto and picoampere, right? Remember the first day I was telling you SPICE, or the Cadences SPICE, puts a resistor in parallel to every node to simulate the circuit. The resistor it puts is a 10 to the power 12 ohm resistor. Okay, it calls it G min. It puts in a conductance of 1 to 10 to the power minus 12. Now think of it this way. My current is 1 picoampere. Okay, and I have got a resistor in parallel of 1 10 to the power 12 ohm. It already produces a 1 volt drop across that. So it's not the physical circuit which causes the problem, it's the Cadences simulation which causes the problem. So to match that, we have to manually go and change the G min for simulation. I will show you how to change the G min in analog simulation later on once you have reached that. Okay, doc? So that's the lecture part of this theory, which also completes the tutorial side which we are doing in morning. Let's start the lab work.